perhaps one of the most widely recognized physicists, Michio Kaku, has shared his insights on this issue. Kaku, known for his remarkable contributions to the field of theoretical physics, has noted that the James Webb Space Telescope has observed 6 massive structures that scientists once believed were incapable of existing. These findings have the potential to open up new perspectives on our understanding of the universe. It is, therefore, both fascinating and worth closely examining these developments. Kaku, a prominent figure in the scientific community, is a physicist of American and Japanese heritage. He is regarded as an expert in both classical theoretical physics and quantum mechanics. Unlike some of his more conservative and controversial peers, Kaku has embraced the astonishing recent discoveries of the James Webb Space Telescope, JWST mission. We are fortunate that this esteemed scientist has chosen to break his silence and address what can no longer be ignored. The excitement and profound tone of the physicist are evident in his remarks on the revelations made by the telescope. He suggests that these discoveries have reignited his curiosity. Let us delve into the implications of Michio Kaku's acknowledgement of these 6 colossal galaxies. Kaku is a scientist who has consistently demonstrated a willingness to explore new hypotheses throughout his career. He appreciates that Einstein's theory of relativity and Newton's laws are insufficient to fully comprehend the universe's vast complexity. Kaku understands that the discoveries of the new telescope could significantly advance the field of science. However, many of his colleagues have been reluctant to accept this view, causing concern and unease among both proponents and critics of quantum mechanics. Despite this, Kaku finds humor in the situation. The JWST has revealed 6 gigantic galaxies dating back to the earliest periods of the universe. Each of these massive galaxies contains more stars than our own Milky Way, despite forming only a short time after the Big Bang. The group of cosmologists responsible for the discovery has named these systems universe breakers, as their existence challenges our entire understanding of the cosmos. Something here does not align with the Big Bang theory. According to this theory, the universe was a chaotic place following the initial event. The first solid objects required several 100 million years to form, and it took countless additional years for these objects to achieve sufficient density to emit light. The development of complex structures like galaxies was supposed to occur much later. Yet, some of the newly discovered galaxies are larger than the Milky Way. Their immense size and brightness suggest they were possibly forming new stars at an extraordinary rate, several stars per year, while our own galaxy forms only 1 star annually. The precise timing of the formation of the first galaxies remains uncertain. Scientists have only recently begun to explore this question. What is clear is that, in the beginning, there were likely only single stars or small groups of stars that eventually merged to form progressively larger structures. This process ultimately led to the formation of dwarf galaxies, which underwent mergers and gradually evolved into larger systems. According to existing theories, highly advanced and massive galaxies could not have existed at such an early time, raising questions about whether the universe is older than previously believed or if complex large-scale structures existed much earlier than theorized. This current situation poses a challenge for conventional science, which struggles to reconcile these findings with established models. Furthermore, some areas of physics have firmly rejected this discovery, citing potential errors in the age assessments. Aware of this skepticism, Kaku remarked, "There are numerous cases of outdated and misleading theories that persist due to the popularity of certain experts. Many of these theories were ultimately disproven when careful analysis revealed their flaws. Therefore, the essential work in any science, particularly in physics, rests with the experimentalists, who uphold the integrity of research through rigorous evidence. On Earth, we have very limited knowledge of the true origins of the universe. The Big Bang theory was established in 1927 based on observations of the universe's expansion. This information led to the conclusion that the universe began as a singular point and has been expanding ever since. At the time, it was difficult for both the public and scientists to imagine a universe with a beginning and an end. The idea of a universe that had always existed seemed more plausible. Over time, however, the Big Bang theory gained widespread acceptance as more evidence supported it, such as the discovery of cosmic microwave background radiation and the observed redshift of galaxies. Yet, the recent discoveries by the James Webb Space Telescope challenge the theory in unexpected ways. The detection of these massive galaxies so early in the universe's history raises questions about the timelines and processes we have long considered foundational. The universe breakers defy the expectation that galaxies took hundreds of millions of years to form and mature. If these structures existed shortly after the Big Bang, it implies that either the conditions for galaxy formation were vastly different than previously thought, or our understanding of the universe's early development is incomplete. This revelation could indicate that star formation and galaxy assembly occurred at a much faster rate than existing models predict. These findings also compel us to revisit fundamental questions. How old is the universe really? Is our understanding of dark matter and dark energy, key components of cosmological models, accurate? Could there be unknown physical laws or forces at play during the universe's infancy? For Michio Kaku, these questions exemplify the beauty of science, its capacity to evolve and adapt as new data emerges. While some scientists remain skeptical, emphasizing the possibility of errors in data interpretation or instrumentation, others view the JWST discoveries as an opportunity for revolutionary advancements in cosmology. If these findings are confirmed, they could lead to new theories that replace or extend the Big Bang model. Such theories might incorporate faster mechanisms of galaxy formation or redefine our understanding of the universe's early conditions. For Kaku, the implications are profound. As a physicist who has long pushed the boundaries of theoretical frameworks, he sees these discoveries as a call to rethink the foundations of physics. In his view, science thrives on the willingness to question, test, and revise. The universe breakers are not merely anomalies to be dismissed but clues to deeper truths about the cosmos. In summary, the James Webb Space Telescope has unveiled a mystery that challenges our most established scientific theories. Michio Kaku's insights remind us that science is a dynamic process, where the unknown serves as both a challenge and an invitation to explore. As researchers continue to analyze the data, the universe breakers may prove to be the key to unlocking new paradigms in our understanding of the universe. Furthermore, the vastness of time was beyond the human creative mind. As a matter of fact, even today, analysts face hardships in understanding it. In any case, it is critical to re-evaluate these potential outcomes. These new insights don't align with what specialists have relied upon for years in the hypothesis of how things came to be. All things considered, science has repeatedly shown that reassessment and openness to bold ideas are fundamental aspects of the scientific process, just as much as the validation of specific theories and observations. When Einstein was a young scientist, he believed planets were fixed in the universe, and these specific ideas included a defined space. However, we now understand that everything in the universe is moving. Planets orbit stars, stars move within their galaxies at varying speeds, and entire galaxies move rapidly through space. The ultimate fate of the universe remains unpredictable even today. Researchers are challenged to accept uncomfortable discoveries and recognize that theories are not merely guesses or grand ideas until they are rigorously tested or confirmed through undeniable observations. The possibility of the Big Bang arose from evidence showing that galaxies are moving away from each other, with their distance proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding for a long time. Additional evidence, such as cosmic microwave background radiation, the redshift of light from distant galaxies, and other cosmic patterns, seems to support this hypothesis. However, it is crucial to remember that those who once believed the Earth was flat or that the Sun orbited around us also had similar evidence for their doubts, until events or technological advancements provided a clearer picture. Today we are witnessing a similar situation. Researchers expected the James Webb Space Telescope, JWST, to validate assumptions about the Big Bang. Instead, they discovered 6 systems that appeared too massive for their age. This reminds us that science constantly evolves, and experts must remain open to new discoveries and re-evaluate existing theories based on available evidence. Scientists use redshift as a tool to make specific measurements in studying the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, imagine watching a car approaching you. As it gets closer, the engine sounds louder, but as the car passes and moves away, the sound changes. This happens because the sound waves shift as the car moves. The same principle applies to light. When a light source, such as a distant star, moves toward us, its light shifts toward the blue end of the spectrum. Conversely, when the light source moves away, the light shifts toward the red end, a phenomenon known as redshift. Physicists have converted redshift values into speeds and distances for studying quantities in the universe. However, it is vital to note that small errors in these calculations could have significant implications. The assessment methods used in the past are now under review, and the conclusions scientists draw regarding the latest discoveries related to our universe are exciting. It is essential to determine whether these results are genuinely based on redshift miscalculations, or if some researchers are simply denying the facts. This is a question that requires serious scrutiny and a careful review of the data and methods used in the studies. As scientific inquiry advances, discoveries made using instruments like the James Webb Space Telescope often challenge our assumptions about the universe. The recent discovery of 6 massive galaxies dating back to the universe's infancy is one such example. These systems, which defy the standard theory of galaxy formation, raise significant questions about the timelines and processes involved in the development of large-scale structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with advanced technologies that allow it to peer deeper into space with remarkable clarity. Its ability to detect light from the farthest reaches of the universe provides astronomers a window into the past, enabling them to study galaxies that formed billions of years ago. The discovery of these ancient massive galaxies challenges existing models, which predicted that such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond cosmology into fundamental physics, compelling researchers to rethink established theories about the early universe. These findings also underscore the importance of remaining open to revolutionary ideas and updating our understanding based on empirical evidence. Michio Kaku has emphasized the critical role of scientific validation in shaping our perspective of the universe, noting that theories must evolve continually to accommodate new data. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, supporters argue that the discovery of early massive galaxies suggests a longer timeline for galaxy formation than previously thought. This perspective challenges the conventional view that galaxies evolve slowly over billions of years through mergers and the gradual development of smaller structures. On the other hand, skeptics caution against quickly discarding established models based on limited observational data. They advocate for a more cautious approach, suggesting that discrepancies in data interpretation or measurement errors could explain the surprising findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a critical role in these key evaluations. As galaxies move away from Earth, the light they emit shifts to longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy's light spectrum, astronomers can determine its distance from Earth and its velocity relative to us. This information provides crucial insights into the expansion of the universe and the dynamics of galaxies. The combination of redshift data and advanced telescope observations has led to remarkable breakthroughs in understanding the universe. However, new findings such as the 6 massive galaxies identified by the James Webb Space Telescope challenge the current understanding of cosmic evolution. As the scientific community continues to evaluate and refine models of galaxy formation, these discoveries highlight the ongoing interplay between theory and observation, where new data have the potential to reshape our understanding of the universe.